Hey there, Geometry Genius. We're going to move ahead, starting one of my personal favorite sections of geometry, Pythagorean Theorem and right triangles. This also will cover the converse of the Pythagorean Theorem. In this section here, you're introduced to the Pythagorean Theorem and its converse. We'll be able to find unknown side lengths in right triangles using that theorem. Given three side lengths of a triangle, determine if it's right, acute, or obtuse. Determine whether three numbers are considered a Pythagorean triple, and also use Pythagorean theorem to solve word problems. So let me give you a quick idea of what Pythagorean theorem is all about. So Pythagorean theorem allows us to take any right triangle and get a hold of the sides. So in this case, although it doesn't look as if these are going to be actual length segments, this is considered a 3, 4, 5 Pythagorean triple and visual of it, where if we look closely, the area from B to C is claiming to be 9. So what do you think the length of B to C is if this is a square? You should be able to say this is 3 from B to C. If this is 16, what do you think A to C is? You should be saying 4. And then B to C, what do you think the length of A to B is going to be? The hypotenuse. You should be saying 5. So this is a visual of how Pythagorean theorem works, where if we keep one of the angles 90 degrees, let's see if we can do this. Stretch this out a little bit. We can end up with tons of answers that would retain the fact that this is a right triangle for angle C. So notice that I changed up some of the side lengths, and that's okay. So Pythagorean theorem allows to take a right triangle with a right angle and assumes that if we take one of the legs being squared and we add that to the other leg being squared, this should be equal to the hypotenuse being squared. But normally we just say, a squared plus b squared equals c squared. A and B are measuring the legs of the right triangle. So that's really important to recall. So we'll kick these off. We'll get to it with some examples. With a Pythagorean triple, these are pretty common to come up, where these are given as definite right triangle lengths. Where if we were going to test these out, well, let's try it. 3 squared plus 4 squared should be equal to 5 squared, which is true, because 9 plus 16 definitely equals 25. We could also see the same thing for 5 squared plus 12 squared equals 13 squared, which makes sense because it's 25 plus 144, and it equals 169. So these sets of side lengths come up quite a bit. So anytime you see these numbers, be on the lookout. You can claim that they are a Pythagorean triple. And we'll see some of these as we move throughout this chapter. First example has us finding the length of the hypotenuse using the Pythagorean theorem. Write our answer in simple radical form. Well, I know that 8 is a leg for sure. 10 is our other leg. We have our hypotenuse, and that's what we're trying to solve for. So whenever you get stuck, try to label out what you know, what you don't know. That will definitely help. So if we take 8 squared plus that 10 squared, this should be equal to 64 plus 100. We'll call this c squared for their hypotenuse. So 64 and 100 should be equal to the hypotenuse being squared. So 164 equals c squared. We can break this down further. Well, let's see. If we take a square root, square root of 164, you could probably think that out with a calculator, but I'm confident it's divisible by 4. And 41, I want to highlight on the 4 because that's a perfect square. We can rewrite that pretty easily. So we can rewrite this measurement as 2 square root of 21. for the hypotenuse C. Pretty simple. Now if we work backwards and have the hypotenuse, we would claim now that 20 squared should be equal to the 8 squared plus that x squared that's missing. So this is going to be 400 equal to 64 plus x squared. If we get rid of that 64, this should be what? 336 equals x squared. Square root of that, whatever it might be. I forget off the top of my head. Jeez, what would that be? 56? 56. Sorry, I'm just thinking out loud with sixes and how we could break this down further. Yeah, I mean, honestly, we could just leave it as x equals the square root of 336. And if we were going to use a calculator to get an approximation of this, that's always a good look. So if we take 336, take that square root, approximately 18.33 units. Pretty simple. I'll leave you with this final word problem here where we have a walkway that forms one diagonal of a square playground. Well, they mentioned a square playground, so I'll try to visualize this. Square playground. The walkway is 24 meters long to the nearest tenth of a meter. How long is this side of the playground? Draw a diagram and solve. Well, I know that the diagonal of the square would be measured like this. It's 24 units. And since this is a square, what do we know about these four sides? Well, they should be congruent. So let's call one of these sides S and S. And trying to find a side of the playground, we could say that S squared plus S squared should be equal to 24 being squared. We can say this is 2S squared equals 24 squared. What's 24 squared? Let's find that out. It's 576 over 2S squared. S squared in this case is going to be equal to 288. And if we take the square root of 288, that's a big part here. We've got to take square roots, and we'll take the positive version of it. This looks as if it's approximately 17 units. So 17 meters in this case. Pretty simple. A little tricky to graph out. In class, I'll go over how to determine if we're dealing with an acute scalene or isosceles triangle. Hope this was helpful. If you have any questions, please let me know if I can help. Thanks for watching.